Yeah, I'm not sure.
Are you ready to go, Tom?
Yeah, I'll keep talking.
Alright, ready?
Yeah.
Go.
I'm going to try and tell you about water and the science of it. I'm way out of my depth, but then again, the scientists are too. I'm going to need to read from this. The full air ring, which is not mapped. We are presently only exploring its fringes. Okay, we are all mostly water, as is our world, and we only understand life through water. Okay, it's all about love and hate. Okay, water is full of a strange and sticky love, with the curious twist of hate. And because we live in this ideal climate, we have the privilege of having the three phase stages of water, which are gas, liquid, and solid. It's very important. Now, water is an extraordinary thing. It's got strong and weak attachments. It's very strongly attached to itself, but it's loving to attach to other things in kind of groovy but slightly weaker way. Okay, but the most important thing is it's got this special geometry that is bent, which with this covalent bond, which gives it another. What we're looking at is invisible. Wavelength of light is this big. These things are that big. We'll never see them, so people have to imagine them. Ever since Heisenberg's uncertainty principle, we realised that you can't really see the electrons, you never know where they are floating around, so it's just a kind of cloud of stuff. Okay, ice, the most important thing about this is that there's all kinds of different forms of it. You can read that from Australia if you can read faster than I can speak. What's really important is that it floats because it expands as it gets colder, and that means the Titanic will sink. But fishes in the sea will never die because it will never sink. So right, to understand this better, you have to imagine yourself as a molecule of H2O, and if you stand like that, with legs like that, but your arms that way, you get a sort of feel of the geometry of it, and they're fantastic mixers, the greater parties, they fix life in all sorts of different ways because of who they combine with and the way they do it. Okay, this is the most important thing for ice. When all these molecules are, as a liquid, they're working together, and then when they freeze, they go bigger, and that's why the whole thing is less dense and it floats. They're fabulous engineers. Aquafaba, interesting for sculpture. Okay, some of the structures like this, right? So there's these things, they're forming these hexagon structures, which is why snowflakes are beautiful as they are. But if you put them under greater pressure, if we all did this in this room now, they'd be okay. We've had some more chairs and we squashed it, we'd have to make a new structure to maintain that thing. And there's all different kinds of ice, okay? Under different kinds of pressure. Sometimes in the earth, there's all these different structures. Scientists can make these in chambers, and when they change from one structure to another, they make massive bangs as they lock into new configurations. Ice 7 is solid at 100 degrees centigrade, which is 1,000 times the pressure. Okay, this is the start of it. Okay, you've got the temperature in this way, and these are the different kinds of ice that there are because of the different pressures that there are. Not only in our planet, but in other parts of the universe, because water is the most ubiquitous material in the whole universe, the most ubiquitous molecule, okay? Now, there's a couple of very important things about this. Similar chart, temperature this way, pressure that way, okay? Critical thing, you've got, it's weirder than anything else, okay? Because it can go from solid to gas, sublimation. This little critical point here at 4 degrees centigrade is where it does that little expansion thing, where it all starts to float, and you've got the critical thing. Okay, that means that all this, the Earth is breathing, and all this water's flowing around. It takes more energy and heat. Oh, fuck it, where's that? The Gulf Stream brings twice as much tropical heat as to us to make Europe warm as you would be able to burn coal in a year. Okay, the next thing, bubbles. All right, if you ever thought about bubbles, why are they like that? What a fabulous structure. The reason is because these lipid molecules or detergent molecules are hydrophilic and hydrophobic. They love and they hate water. The head loves, the tail hates, and so they love each other. They have to stick together, but they separate out. You saw it there. Okay, all sorts of other things. The way that water interacts with all of its friends around is very different. And quite critical and measurable, which gives some plant structures can repel water. In other circumstances, you've got meniscus and capillarity. Okay, it's a fantastic catalyst, fantastic solvent. This is water, this is salt, which is sodium chloride. Water gets in there, we just take it for granted. But it's very much better solvent than so many other things. Breaks it all up, joins to it in new ways. Okay, as a liquid, it's doing groovy things, making these sort of vortexy things, which are beautiful for sculpture. And oh, this is quite good. When these two bipolar vortices meet together, they actually join and they do that lovely thing as well, which is very photogenic. Next, this is the next phase, which is steam, but you mustn't think that clouds are just steam, because there's ice in there as well. And they're incredibly complex structures. There's these massive superorganisms of all kinds of vortexes and stuff going on. There's a little quote from Shakespeare about it. So it has that. Okay, all life is dependent upon water. Only plants originate matter. Animals just reconfigure it. Okay, and plants do that by taking sunlight, water, and carbon dioxide. This nutrients part is next to nothing. Those are the two big ones, and they make stuff, and we eat that stuff. And all other animals do that as well. Okay, here's some structures. The same molecules can configure themselves all different ways, even like a Buckminster fullerene, which is a dodecahedron-shaped water molecule. Philip Larkin says if he was to make a religion from scratch, he would start with water, because it is so magical. Right, now if you look under your seats, quickly you'll feel a couple of limpet-like structures, and just quickly, you've got 20 seconds to do it, get them out, okay? Hold them up in your ears and they're like gas, okay? Put them together, and sublimate, become solid. Join them to your neighbours, and we'll all make a unique sculpture in 20 seconds. I'll just get them all up.
Who's next?
Everyone a winner. Do have a look underneath, because you might find some rogue ones. Okay, the next one is Graham and Robert. Last chance.
No, it's not very good.
Okay, Graham and Robert.